last day, we had the example of binomial data and ended on the example of a specific scenario with binomial data where you had sort of a known expected response and then a response from the participant, and you wanted to ascertain not only what an effective sum predictor, say group, was on their overall accuracy, but when you have that scenario of an expected response and an actual response, you can have a model that can parse out not only effects on accuracy, but also effects on your overall bias for response, which can manifest, as well as the effect on discrimination, where discrimination is probably what we were trying to get at when we were talking about accuracy. So this discriminability of the stimuli. We ended up with that model that, okay, so we had the scenario where it was like a forensic psychology scenario where you're saying you are a witness to a crime and we're presented a bunch of photos and you're just supposed to identify whether the guilty culprit was present or absent in the series of photos. So you had four groups, a group for which the person was absent and a group for which the person was present, and crossed with that variable was whether the photos were shown to you one at a time in the serial condition or whether they're shown to you simultaneously in the simultaneous condition. And we can model the influence of these two predictors, the expected response and group, on the odds of, or the log odds of responding present. So, for example, if this blue line is all the two groups for which the person was actually present, we can see that there's a higher log odds of saying present, so they're more likely to be accurate in the serial group than in the simultaneous group. Conversely, in the expected response is absent, you can see that there's a higher log odds of responding present, again, values closer to the top of the curve reflect a higher likelihood of saying present. So this would be sort of a higher likelihood of making an erroneous response than in the simultaneous. I wanted to bring this back up because there's a couple more sort of visualizations that are useful. So I showed you the coefficient table here. So it shows the intercept that's on the log odds scale. I told you that the group, the main effective group, was the effect on overall bias. That the main effect of the expected response was the overall discriminability. You expect this to be very non-zero. It happens to be negative just because of the alphabetical order of these two things. And then finally, the group by expected interaction conveys whether, in addition to whatever bias group may induce for responding one way or the other, what sort of change in your discrimination ability does being in one group or the other induce. So we can look at the sort of predictions. Given this table of coefficients, we can get the predictions for each cell of the 2x2 design here. But it's also useful to actually have a couple plots that actually convey these two things. So I thought I'd take the time to do that. So I'm looking at the code from the other day. I'll upload it because we're going to change it. I'll upload it to the 17th folder, February 17th. So I'm looking at the section, visualize the prior predictions for the condition. I'm going to copy this little bit. Oh, actually, I don't need the whole thing. I just need this little chain here. All right. Visualize the effect of group on response bias. Okay, so I want to just get this visualization of group on response bias. So what I want to do is first, I'm going to pull this down. We'll group by group and sample. again, if I look at this thing called CP, it has 16,000 rows and 5 columns. There's a column here indicating samples. So for each combination of the conditions, we get a sample from the posterior. And there's, I think, 4,000 samples from the posterior. So for each group and sample, we want to summarize. Sometimes I spell it the American, sometimes Canadian, or British. So let me just ask you, if I've got this data set CP that has group, expected, sample, value, and I run this little chain on it, what is this chain doing? What should the result be?
It should give you the mean for the expected response for each of the conditions.
Mean for the expected response? Let me actually show you the first little bit of it. So expected response is no longer there. What we're doing is for each group and sample, we're averaging across the two values that reflect the two expected response conditions. So here's a serial absent has a negative 1.18. Serial present has a positive 2.16. And we're just going to get the average of those two numbers. So it's like saying, what is the likelihood, or what is the log odds of saying present, regardless of what they were expected to say?
Oh, I thought it was grouping by group.
Yep, we're grouping by group. So anything that's not in this group by gets average over. So we're grouping by group and sample. So we're therefore averaging over any of the other columns. So we're averaging over expected.
Okay.
So having done that, now I can pipe to, again, another group by where I say, okay, ignore sample and compute these summaries. So now it's going to be a bit of a reduced plot compared to what we had before. Probably don't need the line.
Can you just go back for 1 second? I just want to try to understand what's happening when we group by group the second time. Maybe if we go down to where the table is.
Okay. So this still has, let's go down here, still has 8,000 rows for each sample in the data frame.
Okay.
And for each group, there's 4,000 samples. So what we're going to do is now group by group and compute across sample now. What is the median sample? What is the 2.5% sample? And what is the 97.5% sample?
And if we had just group by group initially, then we wouldn't have gotten those comparisons between the sample, like within sample first.
Yeah, we would have been averaging across sample as well, and then we wouldn't be able to compute these intervals across samples. So this conveys the sort of magnitude of bias in each of the conditions. 0 would reflect 0 bias. So in fact, there's bias in both conditions, it appears. And we could go further and actually ask, okay, what's the difference score? What's the distribution reflecting the difference between these two conditions on bias? But that's right there in our table in the first place. You'll notice that these two dots are about, I think, what did it turn out to be? 2 something. Oh, no, this. Yeah, 2.1. So that looks smaller than 2. Oh, no. Yeah, it's about 2. Because that's 1, that's another 1, and it's a little bit more. Yeah. So We could go ahead and do the difference score and get that as a spit out from a dplyr, but that's already in the table right here. So yeah, this is another way to take this original graph showing the probability of response in each of the conditions and simplify it to something that is actually talked about in this table, but you're actually getting the original values. So you can also see this sort of other phenomena that both groups actually have non-zero bias. So one condition induces one type of bias, the other condition induces another type of bias. And we can do the same for, so here's our code for visualizing the effective group on response bias, what we just did. To visualize the effective group on discriminability, it's kind of shown in this original graphic where like the distance between the blue and the red reflect the discriminability. So you can see that there's increased, well, this has lower discriminability than this one. But it'd be nice to actually have just like a 2-point plot with the error bars to actually see that. So we're going to copy the code for doing the bias and paste. And I'll go up to the top of the list. Visualize the effective group on discriminability. So we're still going to group by group and sample, but this time for each combination of group and sample, we're not going to average across the two values. We're going to get their difference. So what is the difference between these two, and what is the difference between these two for each sample? But otherwise, the rest of it is the exact same. I'm going to, just for if you guys are looking at this afterwards, change this to response bias so that the axis actually reflects the proper thing. And here I will talk about discriminability. So there's our plot of the difference between the two conditions in their discriminability. Or, well, the two conditions' individual discriminabilities. Ideally, so if you had one of these overlapping with 0, that would actually suggest that that condition, people in that condition weren't sensitive to the properties of the stimuli that they're supposed to respond to. So ideally, you don't want that in your data. This obviously is showing that it's non-zero, but one is different from the other. We could go ahead again and actually compute what is the credible interval for this difference. But again, that's in our table from the last line in the table reflecting the interaction. 2.53. This is around 2. This is around 4.5. So yeah, 2.53 is about the difference between those. So that matches up with what I'm asserting to you. So just a couple extra plots to that you would probably want to convey to your readers if you had data like this. And of course, I only had this set up for just 2 groups, but because this is the regression code, you could have any number of variables that you're asking about, and each one, its own main effect, would reflect the effect it has on bias, and each one's interaction with the expected response would convey its effect on discriminability. All right, so I'm going to save that and close and come to our next example, which I've already opened up and started doing things because it was sampling rather slowly, so I wanted to get it done before we got here. So we've talked about binomial data. Next week, we'll talk about multinomial data, where there's not just 2 categories, but maybe 3 or 4. I'm still wrapping my head around that, so I'm going to need to take the weekend to work out how sort of how to describe it to you guys. So in the interim, I thought I'd talk to you about count data, which is fairly common. The example I have here, I'll start from, so I've got, again, just to show you in my Finder, in today's folder, there's a binomial 2, so that'll have the updated code from what we typed today, and we've got the count folder. So if you double-click on the count rproj, it'll bring it up, and the count.r file is already here. So I'll start from the top, even though I've already kind of started over here. The count.csv is the data set we're dealing with, so let's take a look at it. So I've got 2 columns here. One column called species that has rat and lots of rat. Oh, haha. I forgot that I made it when I was playing with it. I made each species have 1,000 observations. That's probably a lot more data than you guys will ever collect. So yeah.
That part of why it probably took so long to.
Let me take a look. No.
Okay.
No, it shouldn't. Usually these things are pretty fast. Until we get to hierarchical models, these models should be fast regardless of the amount of data you have. So yeah, I erroneously have 1,000 rats and 1,000 mice. I meant to have 100 rats, 100 mice. And the way I've conceived of this data, the sort of experiment it came from, maybe you're looking for the presence of plaques in the brain. And so you've got people literally counting things in the brain. So this plot over here takes a look at the 2 populations, your mouse population and your rat population, and the distribution of counts that were observed. So there were over 100 rats with 0 plaques. There were like less than 50 mice with 0 plaques. There were over 100 mice with 1 plaque. There were like 250 rats with 1 plaque, etc. So this is very common data, I have noticed, where you have this like hard bound at 0 and integer values for the actual observation. And I've often seen it sort of submitted to things like Gaussian models that it's like nails on a chalkboard for me, because this is a I guess, established realm in statistics, i.e. how to deal with counts data. So there's 2 main ways to deal with count data. The first main sort of model for count data is the Poisson model. I can give you a feel for how Poisson looks, which I'll just do here. There's an rpois function. So let's generate a lot of data. So the rpois, if we look at it, let's get the help for rpois, and it looks at the Poisson distribution. And the rpois has the Poisson distribution has a single parameter. Let me pull up also my notes. So without even knowing what this single parameter is, we could just punch in some values. So what if we put 1? And we'll do a histogram. I'll use the base R plotting functions just for simplicity here. So here's a histogram of when that whatever that parameter is 1. Let's go make it 0.1. Okay, let me actually make this from equals 0 to equals, I don't know, 10, so we can see a little bit better. Oh, no, you can't do that. See, the base plot functions are so irregular. Xlim equals C 0, 10. Okay, so when it's 0.1, it's quite shoved over. When it's 1, we get a little bit more. Let's try 2. Get a little bit more shoved over. Let's go double 4, even more. So this parameter seems to be related to.
Ones.
Sorry?
It seems like the Weeble ones for that.
Yeah, it's similar to Weeble. It's shifting the distribution over. It's also kind of changing its shape a little bit as it goes.
That's more what I was thinking of.
Yeah.
But
So this single parameter seems to be affecting like both the mean and the variance and the shape. So it actually happens that if the data is from, let's actually try a few things. Mean, actually let me say, x equals that. Let's get the mean of x and the variance of x. So if the value is 3, we get a mean of 3 and a variance of about 3. Let's put it at 0.1. If the value is 0.1, we get a mean of about 0.1 and a variance of about 0.1. Okay, there's a little bit of a pattern here. If the value is 10, we get a mean of 10 and a variance of 10. So this parameter seems to be specifying the mean that it's going to generate, but in a way that's not Gaussian, because it actually specifies both the mean and the variance. There's actually a formula for the Poisson distribution. It's lambda to the power of x times xe to the power of negative lambda divided by x. Anyway, it's a complicated formula. All you really need to know is that this is like the conventional thing that is used to model count data. It has some sort of, using a Poisson implies some assumptions. So you can think of that parameter, lambda, as being a rate parameter. It's the mean sort of rate at which something will happen during a given amount of time. So presumably, if you're thinking about this in terms of time, you set your experiment up, if we're talking about these mice and rats and plaques, you set this experiment up so that you're sacrificing your animals after a fixed amount of time, so that they're all experiencing that fixed amount of time, and you're then just counting the number of plaques that manifested during that time. You can actually have other things where the count is happening through time, so the mean, the count of times that a rat pressed a lever during some sort of behavioral conditioning experiment. So the counts actually occur at discrete time points during a specific session, but the thing you get at the end is just some number of times that they put. So the assumptions of the Poisson are that, let me pull this over. Okay, K, so, the count that you observe is the number of time an event occurs in some interval, and K can take any value bounded at 0, so you could have a scenario where you didn't observe anything, but could take on integer values, 1, 2, etc. Another assumption of the Poisson distribution is that the occurrence of one event does not affect the probability that some second event will occur. This actually is a somewhat sort of untenable assumption. For example, if you're counting spike trains or something in neurophysiological data, we know that it takes time for a neuron to actually recover. So an event happening actually does influence it happening again. But in a lot of cases, like maybe a plaque growing and the amount of times that a plaque happens, it'd be hard to think of a sort of causal mechanism by which one plaque manifesting reduces the likelihood of another plaque manifesting. So there are many scenarios where this assumption is okay. The rate at which events occur is constant. So if you have a scenario where the risk of plaques increase over the time course of your experiment, then the Poisson distribution isn't going to sort of adequately describe your data. I'll have to think about why. So I'm not sure. Two events cannot occur at exactly the same instant. that makes sense. So they can't press a lever twice in one instant. And right, the probability that an event in a small interval occurs is proportional to the length of the interval. So you kind of expect low counts if you observe for only a little bit of time, higher counts if you observe for a longer amount of time. Yep.
So you said you're not sure why, or where the assumption about rate constancy really comes from.
What that would drive in terms of a different distribution?
That's what I meant.
I'll have to
It's
think about that.
It's like if you know how much tolerance does it have for non-constancy?
Yeah, because I mean something like, I don't know, if you've got like an Alzheimer's model of rats, you'd expect that there'd be sort of like an exponential increase through time of the manifestation of plaques. So that would seem to violate that. But I don't know like what the consequence of that is.
Yeah, that's been
whether it could actually just be modeled in.
When I've used that when I've thought about using Poisson for count data, that's always been the issue, is that it's always at a super non-constant rate. And I didn't know to what extent.
My intuition is that it's going to drive what's called over-dispersion. So if you've noticed, with the Poisson, it's always the case that the data, you expect the mean to be approximately equal to the variance. If the data don't satisfy that, like if your variance is like quite a bit larger than the mean or quite a bit smaller than the mean, then, and usually it's quite a bit, you can only model larger variance. Then you need to adopt a different model, and I'll talk about that in a moment. But we've got the Poisson distribution. It's got a single parameter that we want to do inference on. So I've got a file in here, regression Poisson.stan, and it's pretty much should be fairly similar to what you've come to expect from regression models so far. You've got your data declarations where you tell it how many sort of observations you have, how many predictors you have, then you give it your observations and you give it your predictors. Just like the binomial model, you're passing in, you have to declare y as this int y and then the length. Previously with Gaussian data, we could say vector length y, but here, this is like the binomial case where you have to be explicit ahead of time that y is just filled with integers. That's what counts are. Got a parameter section where we have just a vector of length nx, so nx being the number of predictors we have. So we'll get a coefficient for each predictor. I've called it coef log to convey that, if you remember way back, we the parameter that's supposed to be here has to be positive. If you remember way back when we created a regression model where we allowed there to be inhomogeneity of variance, we modeled the effect of each predictor on the variance, or on the standard deviation. I used this trick of exponentiating that multiplication to make sure that the term was positive. That's exactly what we're doing here. So we'll be looking at the log rate. So if this parameter is supposed to be the rate, and we are expressing the coefficients on the log scale, and we're saying, okay, it's got a normal distribution on the log scale, very wide normal distribution. This is a pretty extreme value for the standard deviation of the normal distribution that we're using to express our prior. This becomes, if we're exponentiating something that's on the log scale, then it's just the rate scale. So if we're exponentiating a log rate, then this expresses a rate. And of course, instead of normal or Bernoulli logit, now we have Poisson to say that y is distributed as Poisson. And in the generated quantities for our posterior predictive check, we're using Poisson RNG instead of normal RNG or Bernoulli-Logit RNG, and we just use the exact same thing that's inside. So I've actually already run this model, so I'm going to copy this bit. It's just going to show you graphs you've already seen. Copy this bit to make sure that X has been created. I've actually already run this bit, and I don't want to do it again. If you ever have that scenario, we've got a model that takes a long time to compile and run, and you just want to save the output so that next time you come, you can use the save command. The first argument is the thing that you want to save, and the second argument is called file, and you just name it. Having saved it, I can then say load, and you just give it the name of the file that you want to load.
Does that go into like a file in your folder?
Yep.
In your directory?
Yep. So there's something called post-Poisson our data. Oh, actually, I don't want to run this because I think I haven't saved the result that I did just a second ago, and I called it post. It will. So it was named post. I saved it into a file. If I load that up again using load, it will create a new object called post. It sort of maintains the object name. But I've, in the interim, created a new thing called post that I don't want to lose. So I'm going to go down and make sure the next model gets saved. There we go. Okay, so that's being saved. I can now go up and overwrite it. Okay, so I'm loading in the post Poisson. You can even look in our environment, and there's this thing called post. So we've got that single parameter, coef log. It's a vector of coefficients. It's got an intercept and the effective species. So the intercept is saying like what the overall rate is. The overall log rate is about 1. And the effect of species on log rate is about 0.5. As you get, just like with the binomial data and the logit scores, the log odds scores, as you get more familiar with, or as you do more data analysis with counts data, you get more familiar with what like log rate and rates actually convey. The rate actually conveys the mean count you'd expect during the period of time that you actually observe. So we can use the get condition post to look at the posterior predictions for each condition. So again, this is the log rate. Rats had a lower rate than mice. And if you want to actually explicitly get out that rate, not the log rate, you can create a new column in CP that's the exponentiated version of what was in the value column. Because if value is log rate, exponentiating that value creates the rate. Show that. So the mean for rats was about 2.25. The mean for mice was about 3.5-ish. Let me actually see. Does that correspond with those distributions? Yep. You could kind of, like if you actually, let me actually say. Gonna say A is our data, right? Yeah. Pipe that to group by, and we'll group by species. Deploy or summarize. I'm just making sure that the actual means in the data correspond with that. Equals mean count. Yep. So the mean in the data was 3.4, 2.1, and the means in the posterior are again pretty close to that. Yeah. we can take a look at the posterior predictive check. Again, the model actually predicts, or we're modeling this as Poisson distributed counts, and it's actually generating, given the sort of credible values that it's generating in the posterior. Let's just generate some data. This actually might be why it took so long. This, because it was having to loop over 2,000 things to generate that. So we can just run our regular posterior predictive check code. I suggest that, so I had shown you that with the Gaussian data, it's good to have a posterior predictive check on the mean and the standard deviation, and I gave you like a normality function to use. You don't expect that this data will be normal at all, so it doesn't make sense to do a test on normality. It does kind of make sense to check the standard deviation, that the model can generate data with a similar standard deviation as you actually observed in the data. We can see the output here again is the percentile that the observed data falls within the distribution of simulated data. For the mean, it falls right in the middle, which is great. For the standard deviation, it doesn't so much. I'm a little curious about that because I generated this data from a Poisson. So,
This isn't the first time, though.
No, yeah, exactly.
I generated it from this model, and it doesn't fit the model.
Well, you know what's, though, if I'm using this 50% credible, I really only have a 50% chance of either of these falling within 50% credible interval. So if you think about it, I'm saying I'm flipping a coin once, and it didn't come up heads, and I'm flipping a coin another time, and it didn't come up heads, and I'm getting dismayed about that. Maybe not a big deal, because 2 heads is a sort of relatively frequent outcome with 2 flips. So, yeah. If you... We can also... Let me actually get... Where's my code to do the means? Let's also do the standard deviations. S equals SD count. Oh, they actually are. Oh no, the variance is the same. No, the standard deviation should be the same, right?
I thought it was the variance.
You're right. Yeah, okay. So, I mean, they're super close. I want to show you a scenario where, well, but the Poisson is super popular for dealing with count data. Even more popular, though, because it's a little bit more flexible, is what's called the negative binomial distribution. You can think of the negative binomial distribution as a Poisson that could be a little bit fatter than normal. So it actually has 2 parameters. One, again, is the mean rate, which is the thing we're probably most interested in, and another parameter that specifies the over dispersion, sort of how much fatter it is. So let me go down to where So I've got this other model, the negative binomial model, and negative binom.stan, and I'll make this big. I guess I'm going to pop it out. All right, so in terms of data coming in, it's the exact same as the Poisson. Y is coming in as an array of integer values. I told you it's a more nuanced model. It has 2 parameters. So in addition to the log mean rate, it also has a thing called phi that indicates the over dispersion. Oh, I didn't put a prior on phi. That's probably why it took so long. Maybe. So let me put a prior on phi.
Why would it take longer if you didn't? What is Sam doing?
It means that it's exploring. It's trying to explore an infinite size space. Now it has some tricks to try to get around that, but it means you're exploring very unlikely areas of the parameter space, and that ends up causing wasted time. So phi has to be positive. So does the rate. The rate has to be positive, and phi has to be positive. So again, you'll see over here for phi, we're exponentiating it. I'm actually making it, this is sort of a heterogeneity of variance model where I'm actually saying the predictors will influence the magnitude of phi. So that's why why this thing is a vector of the same length as the number of predictors. So that's each predictor can influence the amount of over dispersion. Notice over here I'm actually not exponentiating this. That's because this neg binomial 2 log by default expects the value in this slot here to be on the log scale. It automatically does the exponentiating itself. It can do it faster, so that's why I use the neg binomial 2 log. There is a neg binomial 2, in which case I would have to put the exp around it, but because neg binomial 2 log exists, it automatically does the exp part. And the generated quantities part is the exact same. I just take whatever I have here for expressing what y is, and I put instead of neg binomial 2 log, I've got neg binomial 2 log RNG. And so that allows me to generate fake data. So I actually haven't looked at it since I ran it through. So let's actually see. Load post neg binom. All right. So we can look at coef log mean. And that's too small. Coef log mean. And it's pretty much the same as because we use the same data. And it's giving you pretty much the same. Really shitty effect size, or effective sample size, and really bad R hat. I think that's because when I ran it, let me actually just take a look. No, that's going to give me the full thing.
Could it be because you hadn't had a prior on the phi?
Yeah, I think that's exactly what's gone on. But why does...
So it's a case study instead.
Yeah. I want to get the model. See what... Aha.
Case study.
Yep. Yep, there we go. I forgot to put the prior. So, let's see. So instead... Oh no, that's the Poisson. Close files. Oh, I made it a whole separate window, right. So now that it has a prior, it's probably a pretty big prior if it's being exponentiated. Drop that down to 1. And we'll run that again. And sit around.
Well, I make a comment about the Poisson distribution, which is that it seems like if the rate has to be constant, it's not very flexible. Like, because...
That's why I was curious.
Yeah.
Because, like, I mean, even things like, I do counts of kids playing with toys,
Mm-hmm.
and, like, count the different toys they play with.
Yeah.
And there's no reason to expect that should be constant. Like, as in the different, how often they switch from one toy to the other.
Right.
I mean, I can see where some things would be, like, if you are looking at growth or something like that,
Mm-hmm.
that you would expect it to be. But then if you want to look at growth, depending on, like, maybe a drug inducement or something, or...
I think that the general idea is, like, there's, like, for every moment there's a coin flip, and the weighting of that coin flip, like the probability of heads versus tails, is even through time.
That makes more sense to me. So then if you actually are doing interval sampling, then that would follow.
Yeah.
Because every 15 seconds, say for instance,
Yep.
you'd be making a judgment about what's
Yep.
happening.
Yep.
That makes sense.
Okay, this is going much faster. Yay. Now notice those things are coming up at the same time. That's because I told it to use all 4 CPUs on my machine.
And it's actually doing it.
Yep, and it's doing it properly. Yep. Okay. I also asked it only to get 200 samples from the posterior, just because I wanted to see. So our hat's all 1, effective sample size. I mean, I'd be a little wary, because it's less than 1,000, for like pinning down what the credible intervals are, because a lower effective sample size will diminish your accuracy at saying what the extremes of the distribution are. But for talking about like where the middle is, and sort of this should be fine for us talking about it now. Can look at not only the mean, but log, what I call it, phi. And there does not appear to be a difference between the 2 species in terms of phi. That's pretty thoroughly centered on 0. Has a value of that, 3.58. So we can take a look. Well, if we did this, it would look pretty similar to what we had before in terms of the log rate and then the exponentiated rate. So yeah, if you have a scenario where you suspect over-dispersion, the negative binomial is the go-to. In which case, I'd probably use the version that has the heterogeneity, because the dispersion in the negative binomial is actually related to the mean. So if something has an effect on the mean, you actually expect it to have an effect on the dispersion. So it's probably a good idea to make it this heterogeneity model, because that's like a strong expectation. Unless you had sort of a predictor that had an effect on the mean and an effect on an opposite direction effect on the over dispersion that perfectly canceled out what you would have expected from, then yeah, so I would always do a sort of heterogeneity of dispersion model. And that's actually all I had for you guys today. I wanted to add in the multinomial stuff, but it's a little bit beyond me still right now. I might try to show you survival data. If you think about, so survival data is when you have like, how long did this this individual survive, or like how long did it take until some event happened? So how long did it take for them to die, or how long did it take for them to get better, that sort of thing. And there's actually explicit ways of dealing with that sort of data. The other kind of non-normal data, so I told you about categorical logit as just an extension of the binomial scenario. I understand conceptually, but I want to make sure I understand what the code is showing. The ordered logistic is what we would be familiar with as in terms of Likert scales, where you have something where there's discrete categories. You're not willing to make the assumption that like a value of 2 is twice as much as a value of 1. Like they have got an order to them, but you don't know like what the ratios are. And ordered logistic is like the standard solution for that scenario, but there's a couple things I need to wrap my head around for that too. So that's what I'll be working over reading week, is these variety of things. And once we get these, so binomial count, so we've got under our belt Gaussian binomial count. We'll hopefully get survival, categorical, and ordered. In which case, those are all the like kinds of data that are most popular. After that, and we've got regression under our belt for like between subject. After that, we're going to get into, okay, now how do we deal with the scenario when it's a repeated measures design? And how do we deal with scenarios where there's like a hierarchy to the data. So if you've got a rat doing a whole bunch of maze trials, and so they either get to the end of the maze or they don't. So you've got binomial data within a rat. You could compute a sort of proportion completed within that rat, but that's actually a bad idea. A better idea is to use a hierarchical model where you say, okay, each of these many rats performed each of many trials and got a 1 or a 0 in each trial, and let's actually model that as a logistic regression, but have it so that each rat has its sort of success rate, etc. So we'll get into hierarchical models. Hopefully get into scenarios where, like, if you have a continuous variable and you have like a psychometric function, that like a squiggly line function, we'll get into that sort of thing, and maybe some mixture models. Anyway, yeah.
At least 25% of the students in your class, well, right now, would really like to learn more about survival.
Ah,
So
yeah.
very excited.
Yep.